In this lecture, I'll be covering the larger context around deep learning, which are the fields of AI and machine learning, and discuss what it was about deep learning that allowed it to be so revolutionary for the field of artificial intelligence. To summarize, in the early days of traditional AI, computer scientists pre-specified the exact rules for how inputs should map to outputs. Machine learning is a type of AI where the rules for mapping inputs to outputs are not entirely pre-specified, and instead, the machine learning model learns this mapping from data. However, in traditional machine learning, even though the model is learning how to map inputs to outputs, we are still telling the model explicitly what features to pay attention to in the data to use for its mapping. Deep learning is a subset of machine learning that uses artificial neural networks. Unlike traditional machine learning, deep learning not only comes up with the rules for mapping inputs to outputs, it also learns what features in the data it should pay attention to in order to do this mapping. So compared to traditional rules-based AI and traditional machine learning, deep learning models have much increased freedom for the way in which they are solving information problems. Let's show this with an example. So let's say we want to use artificial intelligence to help us identify fruit. The question we want the model to answer is, what fruit is this? With traditional AI, we tell the model ahead of time how features of the object predict identity. So we'd explicitly code an algorithm that says, if it's round in shape and orange in color, it's an orange. Or if it's round in shape and red in color, it's an apple. Or if it's long in shape and yellow in color, it's a banana. So here we have traditional AI where we've hand-designed how we should map features to object identity. Now, in machine learning, we still tell the model what features to pay attention to, which is, here we say it's shape and color, but we no longer tell it the rules for how the values of these features should be used to map to a fruit identity. So instead, we're going to rely on the models to learn what shapes and what colors should be mapped to what fruit. So we've still got hand-designed features, but now the model is learning how features should be mapped to the output. And then we have deep learning, and now we're not even going to tell the model what features to pay attention to. Instead, we're going to feed the model a very naive representation of the data input. So for example, we just give it some pixel values of fruit pictures. And then we're going to rely on the model to figure out what are the features that are most effective for predicting the different types of fruit. The deep learning model is going to figure out for itself what aspect of the pictures it needs to pay attention to, as well as how to map these features then to the identity of fruit. So it's possible that the deep learning model would learn something akin to shape and color for predicting the fruit, but it also will come up with other features that we wouldn't be able to explicitly put names to. So deep learning models with many layers don't just learn one set of features, but actually each subsequent layer of the neural net is learning another feature set that's a combination of the earlier feature sets in earlier layers. And these features will become more and more efficient for predicting the problem at hand, and in our case would be for predicting the correct fruit. So here are some examples of features that a deep learning model for image processing might have learned. As you can see, these features do seem to correspond to things like shape and color. But often it's also hard to explicitly give names to the features that deep learning models come up with. So consider this deep neural network that's been trained to classify handwritten digits. And so this means we have a bunch of images of handwritten digits, and the model has to decide what digit is it given the image we give it. So on the right are the features that the neural network came up with. And these are the features that the neural network thinks are most efficient for identifying what digit was in that image. And we can see that these features do make sense as being relevant for characterizing the shapes found in handwritten digits, but it's hard to put words to exactly what these features should be called. Each subsequent layer of deep neural nets will find more and more sophisticated features that are relevant for the information task that it needs to solve. So here are examples of features learned by a deep neural network for face recognition. So the first layer of the network seemed to recognize light and dark pixels. And then the second layer of the network learned edges and simple shapes. And then the third layer of the network learned more complex shapes. And finally, the fourth layer of the network seemed to learn complex shapes that were very relevant for identifying specific faces. Many of the core concepts for neural networks and deep learning were already in place by the 80s and 90s. So why did it take over 20 years for the deep learning revolution to occur? Well, there are many factors, and there were improvements in neural architectures, learning algorithms, and training methods. But I think there were two overarching reasons why the revolution happened when it did. The first is the shift to training these models with massively parallel computing using GPUs. And this allowed us to train models that were so much bigger than we ever could do before with just CPUs. And the second is the advent of big data. For the first time, we had huge, high-quality data sets with millions of labeled examples, and this was the fuel that these models needed in order to show what they were capable of. I hope you now have a sense for what intelligent information processing means, and how AI, machine learning, and deep learning relate to each other.